Okay. How many people we got here? 9. I thought, there we go. One more. Got 10. I think that's what we were expecting.
Yeah, I think
Okay.
we
So
have.
I'm going to hit record here and hope that that works as well. Let's see. It wants me to sign into Dropbox.
I think
Uh,
that Charlie can record, right?
okay. Yeah, if you're recording, then we're good. All right. Um, so yeah, intro here, or a little bit of background on what I'm talking about. Um, so the way I got involved with the PSE team was I was working on a little pet project after I quit my former job to try to figure out zero knowledge stuff because I kind of saw the opportunity in this space and thought, okay, what can I work on that is, that I can use to learn this space and kind of find the edges of the problems, uh, and also what can I work on that could actually have an impact because I have a hard time learning by just like fiddling with useless stuff. I like to go straight for something that's useful. So I went straight for identity as a problem and the question of how do we in the crypto space make use of the existing identities that people have. There's all sorts of solutions out there right now that are, building new identity schemes, and those are awesome. But how do we use the ones that we already have? Um, and in that space, there's mostly just centralized solutions where you have a trusted authority, like let's say like Gitcoin for their grants matching thing. They have all of these ways that you can verify the accounts that you have, and that the more accounts that you can prove you have on various platforms, or like proving that you have an account on a number of platforms, you can kind of improve your reputation there. So those are centralized where you're really trusting Gitcoin to, uh, do the right thing and not say manufacture identities or something like that. You're also trusting them not to disclose your identity information to anyone. So they know who you are based on your accounts and they could theoretically do something with that information. So those are the sorts of problems I was looking to solve. Um, how I approached that is using this notion of JSON web tokens. What JWTs are is you have, say, like OpenID authentication providers like Google and Twitter and Facebook and all of these social identity providers. But OpenID itself is very like server client and it's somewhat like synchronous. So you authenticate with them and they give you back like some like essentially like a temporary API key to use. But many providers are starting to support JSON Web Tokens, which are um, they are signed credentials or signed claims about your credentials that you can use to authenticate to services. And in particular, you can authenticate to external services that aren't hooked up to that provider's uh, uh, OAuth uh, service. Um, so the way they work is you go to the social identity provider or whatever auth provider and you authenticate with them and they give you back a JSON web token. And I'll get into the structure of that uh, uh, as I go into kind of the nitty gritty details. But essentially, it's a blob of encoded JSON with a signature on it, and that signature is from the private key for the identity provider. Um, So you can take that token and you can go to another service and you can say, hey, here's my JWT. You can see that this JWT is signed with the public key of the identity provider, and it contains these claims like this is the account. So because I know this JWT, you know that I own this account, or I've somehow gotten somebody else's JWT, but there's ways to mitigate that. So it'll say like user ID this, and then you can use that to authenticate operations. So that's the 30,000 foot view on what JWTs are. JWTs look like this. And if that makes absolutely no sense, it's understandable. So it's a bunch of base 64 encoded stuff, because one of the core characteristics of JWTs is that they're highly portable. You can take them around and uh, you know, send them to services, and you don't want to worry about encoding problems. So they're all base 64 encoded. The great thing about this tool on JWT.io is that they provide a decoding of JWTs, so you can see it's got a header which says this is the hashing algorithm. This is the key ID from the identity provider. And then here's the payload with like, here's the issuer, the subject of the JWT. So in this case, this is from my Twitter account. So it says Twitter and then my Twitter account ID, and a few other fields here. So that's what JWTs look like on the inside. And so what I want to do is figure out how to create a zero knowledge proof of this, because sending this thing to, say, like a smart contract to verify is both going to be pretty expensive to do, because in the case of most JWTs, it's like RSA signed. So you take like this, like the header and the payload, and then that gets signed. And so the signature, the RSA signature of that blob is like longer than the blob of data itself. So how do we how do we create a zero knowledge proof of that? You also don't want to like, there might be some fields for some providers that you don't want to disclose, like Google's show your real name. Probably don't want to give that away on chain. So I'm going to narrowly focus in this case on Auth0. Auth0 is basically like an identity provider aggregator, where instead of building support for every individual identity provider and their various schemes, and they might not even individually support JWTs, Auth0 basically aggregates all of those into a single endpoint and a single signing key. Now, admittedly, this does create a trust situation where you're trusting Auth0 not to, say, forge credentials. So that's a caveat here, but for this purpose, it makes it a little simpler to show. And they support like 50 different identity providers, so it covers a lot of the landscape. So yeah, Auth0, you create basically an application, and they give you back some OAuth client credentials, and then you can use that in your application. So let's see here. I'll quickly show my very crude prototype application, which is over here. This is the key data from Auth0. But here's my very crude prototype application. So essentially this, just like for each of the providers, can go through the credential generation process. So let's say I'm going to auth to my Twitter, and because I've already done it, it's not actually going to make me accept it, but it would show like authorize application. And then, yeah, it gives me back JWT. So down here, this is the raw JWT. It's pretty long and ugly to look at right here, but there it is. And here's the breakdown of what it contains. So it's got this key, it's RS-256, so it's an RSA signed SHA-256 hashed token. And here are the claims. There's my Twitter account ID. Yeah, and here's the big, long signature. And then, the masking, I'll get into what I'm actually doing here, but basically here's the masked token. So I only want to disclose parts of it. So I'm only basically showing a couple of chunks of it as public signals for my proof. And these will be the ones, and I'll show you what that actually breaks down to. So simple pretty simple application. I'm not going to run this now, so I don't pick my processor. But if I were to click privately claim it with a zero knowledge proof, it'll run my circuit, like it'll generate the witness for this, create the proof, and you can see some of the proof data in my console here. Might be a little hard to see at the moment, but I'll show it in action shortly. So yeah, I'm gonna get into what the circuits look like and kind of some of the issues that I ran into as I figured this problem out. So here's my circuit. If anyone who's worked with CIRCOM knows that it can be a little tough to coherently describe what you're doing if you're doing something complicated in a zero knowledge circuit, but here it is. The important parts of this are basically generating an SHA-256 hash of the header and payload concatenated, and then masking that out. So we're only disclosing parts of it. So it's a pretty simple circuit at a high level. It goes through, runs some sanity checks on like the parameters to the circuit. One of the things that I realized I needed to do in order to prove these JWTs in an efficient way in a Solidity contract is I needed to densely pack and then unpack my inputs and outputs. So basically, what I do in that respect is I take the blob and I break it up into what I call in the circuit here the segments of data, which are 248-bit signals. So I pack chunks of data into 248 bits. And so instead of passing like individual bytes in, which would be a lot of signals, I just pass in like chunks. And then within the circuit, I take it and I expand it out into internal constraints. So I take it and I convert it to a series of bits that I can then pass into the SHA-256 circuit, and then hash that. It comes out with with basically a 256-bit signal, technically smaller because you can only get like 254 bits out of a signal in CIRCOM. And then I take that and I mask it, and then I repack it into dense signals that are going to be public. The masking part is basically just coming into the circuit is a series, or it's a sequence of true or false signals saying like this segment of the payload will be output as a public output. And I can go into detail on that, but I'm probably getting too deep into the logic here already. One of the big issues I ran into and spent a good couple of months working on was CircomLib does have an SHA-256 circuit, but it is fixed length. And so it can only hash fixed length messages. So you have to know exactly how long your message is going to be that you want to generate a hash for when you compile the circuit. And that doesn't really work because JWTs can be variable length, like depending upon the length of the payload and the header, and depending on a number of things, it could be a wide variety of lengths. So I needed to figure out how to make a variable length SHA-256 circuit. So I took what Circom had made, or somebody contributed to CircomLib, might have even been Jordy, and I figured out that there's an interesting approach you can use for doing like variable length operations, which is, and I've been calling it. So there's this component from, I believe it's from Macy, that they called like a QIN selector. And basically what it does is it takes a sequence of inputs, and then it can, in the case of what I'm doing here, I pass it in what I call the T block. So SHA-256 has 512-bit blocks. So when you pass a message in, you can tell the circuit like, okay, this block is the last one. And then you can use the T block signal to say, you can say basically, is this one of the blocks less than or equal to the T block? And then you can basically for each block, you say like, is this one of the right ones? And then you can like multiply it by that to either get either the block value or 0. So that might be a little bit of a complicated explanation. But anyways, this gives the ability to hash over arbitrary length messages up to some maximum. You have to say like, what is the maximum length, but you don't have to have a fixed length. And then, yeah, it outputs the hash at the block that you specified. Yeah, so there's that was one of the big problems, was figuring that out, and it took me a good long while, but it was taught me a lot of things about how to think about writing circuits. So that was a big part of the process. Another big question was like, okay, I've got base 64 coming in here. And if I recall the logic correctly, it's like 4 bytes of base 64 equal 3 characters. And so I had to figure out how to like mask the payload in the outputs, but with these weird like segments of data that were like 4 bytes in length. So there's a whole area of the logic that has to do with dealing with base 64. And I could go into that, but that was another one of the big problems I ran into, was dealing with weird, essentially like data parsing in a zero knowledge circuit. Yeah, so essentially in goes a payload and out comes a hash and a masked version of the payload. So we can take that, and this is the part of this that just isn't done at this point. So there's, because of how complex it can be to like structure the data going into and out of this circuit and verifying it, the way that this would be used might end up being like highly specific. So if you're using it for, like if one of the examples here for my like verifier contract is